Hey everybody, Mrs. Pesic here. We are looking at section 1.2, Graphs of Equations. Your learning objectives for this lesson, you should be able to sketch the graph of an equation, find the x-intercept and the x-intercepts and y-intercepts, use symmetry to sketch a graph, find the equation of a circle, and use graphs of equations in solving real-life problems. So, little recall. To graph an equation, like you learned in Algebra 1, you would try to rewrite the equation so that one of the variables is isolated, make a table of values, plot points, and connect with a smooth curve or a straight line. So for example, maybe in Algebra 1, you might have graphed y equals 3x minus 2 using a point plotting technique. You would make a little table of values, and you'd say, oh, well, what happens when x equals -1? Well, it's equal to -5. What happens when x equals 0? Well, it's equal to -2, and so on. You would plot those points and then draw a line through them. All right, so let's take a look at another example. What if we wanted to sketch y equals 1 minus x squared? So if we're going to do that, we can make a table of values. Let's just try like -2, -1, 0, 1, and 2. So if we plug in -2, that's going to be 1 minus a -2 in parentheses squared. That's 1 minus a +4, and that's going to be a -3. If I plug in -1, I get 1 minus a -1 quantity squared. That's going to be 1 minus a +1, and I'm getting 0. If I plug in 0, I get 1 minus 0 squared, which is 1. If I plug in 1, I'm going to get 0. If I plug in 2, I'm going to get -3 again. You can check me on those. So -2, if I'm plotting these points now, -2 goes to -3, -1 goes to 0, 0 goes to 1, 1 goes to 0, and 2 goes to -3. And so then I would want to connect these with a nice smooth curve, and this is actually going to be a quadratic function of parabola shape. All right. So solution points of an equation that have 0 as either the x-coordinate or the y-coordinates are called intercepts. So if we go back here and we look at this graph we just did, what were the intercepts? Well, we have this point right here and this point right here. Those would be the x-intercepts. All right, and then we do also have this point right here, and that point right there would be the y-intercept. So x-intercepts are at 1, 0, and -1, 0. And in this case, the y-intercept, there's only one of them, and it occurred at 0, 1. All right, so to find x-intercepts, you can just let y be equal to 0 and solve for x. All x-intercepts are going to be of this form, some number, 0. To find the y-intercept, let x be 0 and solve for y. And so every y-intercept is going to be of the form 0, b. To get a little bit better visual of this, if we had, for example, this line like this, we have this point right here would be the x-intercept. I don't know what that ordered pair is, but I know that I'm going to the left, and I'm not going up or down at all. So it's some number, I'll call it a, 0. And then I have this point right here would be my y-intercept. I don't know what that ordered pair is, but I know that I'm not going left or right at all. So the x-coordinate is 0, and then I'm going up some distance, so I'll call that b. All right, so let's try this example. We're going to find the intercepts of the graph of y equals -x squared minus 5x. Let's start by finding the y-intercepts. To find the y-intercepts, remember you're going to plug in 0 for x. So if we plug in 0 for x, we get y equals opposite of 0 squared minus 5 times 0. Well, that seems to me like we're just getting y equaling 0. So that means that is our y-intercept. All right. If I want to find the x-intercepts, though, I would need to find the x-intercept. x-intercepts, we're going to plug in 0 for y. That was weird how that just popped up. Let's slide that out of the way. So if I'm going to plug in 0 for y in this equation, that'd be right here. So I'm going to get 0 equals opposite of x squared minus 5x. And maybe the best way to solve this equation would be to factor out like negative x. If I factor out negative x, I'll have x here, and then what? Negative x times x is negative x squared. And then I think I would need a plus 5, because negative x times 5 would give me a negative 5x. So remember, I have negative x as one factor and x plus 5 as the other factor. So I just need to set each of these factors equal to 0. I get negative x equals 0. I can divide both sides by negative 1, and I still get x equals 0 as one x-intercept. And then if I set x plus 5 equal to 0 and solve, I would get x equals negative 5 as my other x-intercept. All right, so now let's at least put together what we have found. We have found that the x-intercepts are at 0 and at, I said, negative 5, which is right here. And then we have our y-intercept at 0 also. So this is a y-intercept as well. This graph is a parabola, because it's x squared to 3, 2. We're going to learn that. And it's opening down. So I think that the graph is somehow going to be looking like this. All right? And that's really all we can sketch for this graph so far, knowing the x-intercepts and the y-intercept. Okay, so let's talk about symmetry. Graphs of equations can have symmetry with respect to one of the coordinate axes or with respect to the origin. So let's take a look at this first example. In this case, with this picture, does this graph look like it has symmetry with respect to the x-axis, with respect to the y-axis, or with respect to the origin? Well, in this case, this is going to be symmetry with respect to the x-axis. This x-axis is looking like a mirror, and we've got half the picture above and a mirror half below. So this is symmetry with respect to the x-axis. All right, let's take a look at this picture. Now this one looks like it has some symmetry also, but this time it looks like the mirror would be the y-axis, because we've got mirror images on the right side and the left side of that y-axis. And so in this case, I would say this is symmetry with respect to the y-axis. All right, and how about this picture? This one has symmetry also, not with respect to the x-axis, not with respect to the y-axis, but if I took this graph and I rotated it 180 degrees, I would get back to the exact same graph again. That is your test for symmetry with respect to the origin. All right, so if it passes what I'm going to call the 180-degree spin test, where you rotate the graph 180 degrees, and if you got the same graph, then it passes that test, and that means it's symmetric with respect to the origin. So knowing the symmetry of a graph before trying to sketch it is helpful, because then you need only half as many points to sketch the graph. So let's talk about graphical tests for symmetry. Remember, this was our graph for the function that was symmetric with respect to the x-axis. And the idea with this is a graph is going to be symmetric. Not quite see all of this. Graph is going to be symmetric with respect to the x-axis if whenever some ordered pair xy is on the graph, x negative y is also going to be on the graph. For example, let's say this ordered pair right here was x comma y, then the symmetry of this graph says that this graph is also going to have the ordered pair x comma opposite of y on the graph. If that's always the case, then it's symmetry with respect to the x-axis. Let's take a look at number 2. We had this picture, and this picture was symmetry with respect to the y-axis. All All right, and the graphical test says a graph is symmetric with respect to the y-axis if whenever xy is on the graph, opposite of x comma y is also on the graph. So for example, let's say this point right here was x comma y. Well, on this graph, because of the symmetry, we're also going to have the point opposite of x comma y on the graph. If that's the case, then we have symmetry with respect to the y-axis. All right, and our third type of symmetry was symmetry with respect to the origin. And if that's the case, then anytime you have an ordered pair like xy on the graph, you're also going to have opposite of x comma opposite of y on the graph. So for example, if this point right here was x comma y, then this point down here, that's the kind of the mirror image, if you will, or rotational symmetry, if you will, is going to be negative x comma, or I should say opposite of x comma opposite of y. All right, that brings up algebraic tests for symmetry. The graph of an equation is symmetric with respect to the x-axis if replacing y with negative y gets you back to the original equation. The graph of an equation is symmetric with respect to the x-axis if replacing y with negative y always gets you back to the original equation. All right, so I'm going to have some examples of this in just a minute, but let's take a look at the next part of this algebraic test for symmetry. The graph of an equation is symmetric with respect to the y-axis if you replace x with negative x, gets you back to the original equation. So that's how you can tell whether you have y-axis symmetry. You plug in negative x and you simplify and you see if you get back to the original equation. If you do, the graph has symmetry with respect to the y-axis. And lastly, the graph of an equation is going to be symmetric with respect to the origin if we replace x with negative x and we replace y with negative y, and that gets us back to the original equation. All right, so 3 algebraic tests for symmetry, and let's take a look at some examples. Determine the symmetry, if any, of these equations. So let's start with y squared equaling 6 minus x. If I was going to test for, let's say, y-axis symmetry, question mark. I don't know if it has it or not. I'm just going to test. So that means I would need to plug in negative x or opposite of x anytime I see an x. All right, so let's do that. I'm going to do y squared equaling 6 minus opposite of x. And so when I do that, I end up getting y squared equaling 6 plus x. So is this the same as the original? No. So does it have y-axis symmetry? No, it does not. So let's try that same one with, let's try x-axis symmetry. So I'm going to take that same question and pop it on another page. So now I want to test for x-axis symmetry. All right. It doesn't have x-axis. That's not the one I tested for over here, is it? I can't remember. No, I tested for y-axis symmetry. So x-axis symmetry, question mark. So what am I going to do? I'm going to plug in opposite of y for y. All right, so in my equation, I am going to say opposite of y, quantity squared, equals 6 minus x. Well, negative y times negative y is the same as y squared. So I get y squared equaling 6 minus x. Is this equation the same as the original equation? Yes. So the answer, does it have x-axis symmetry? Yes, it does. And you could try it for the origin, but I think that one's going to be a no-go. All right, let's try this next example. Determine the symmetry, if any, of y equals 9 minus absolute value of x. Well, this one, if I was going to guess, I might try testing it for y-axis symmetry first, and that means I'm going to plug in negative x or opposite of x for x. So when I do that, I get y equals 9 minus absolute value of the opposite of x. But isn't the absolute value of a number the same as the absolute value of the opposite of that number? So I think we're still going to get back to y equals 9 minus absolute value of x, which is the same as the original. So this one has y-axis symmetry. All right, and let's see, I got one more example. This is kind of an interesting example, and you know what, I think I'm going to change my mind on this one. I think I would like to make this y equals, let's do y equals x cubed. That would be x, and I'm just doing this on the fly here, x cubed. Okay, so if I'm going to do y equals x cubed, if I plug in, let's say I'm going to try symmetry, x-axis symmetry. That means I need to plug in negative y wherever I see a y, and see if I get back to the same equation. Well, I get negative y equals x cubed, or I could multiply both sides by a negative 1 and get y equals negative x cubed. That's not true. That's a no. So what if I try to test for y-axis symmetry? Well, then I'm going to plug in negative x, so I'm going to have y equals opposite of x cubed. But that's going to be y equals negative x times negative x times negative x. That's really y equals opposite of x cubed. Is that the same as the original? No. So this is a no on the y-axis symmetry. Let's try origin symmetry. Origin symmetry, question mark. Well, for that one, we need to plug in negative y for y and negative x for x. So then we get opposite of y equals negative x times negative x times negative x is opposite of x cubed. So I get negative y equaling negative x cubed. And if I say I'm going to divide both sides by a negative 1, then I do end up getting y equaling x cubed. I do get back to the original. So the graph of y equals x cubed does have symmetry with respect to the origin. So this is a yes on this one. And if we look at the graph, let me graph this on our calculator for a moment. If I go to new document, no, I don't want to save that. If I go to a graphs page and I just type x cubed, x raised to the third, enter, this graph right here, that would pass a 180-degree spin test, and it does have symmetry with respect to the origin. Okay, so those are some examples of graphical test for symmetry. All right, so let's talk about circles. Now, we already looked at this for our TI project, but let's just review. The distance from point xy to hk is going to be r units. So if we want to use the distance formula, we could say that r is always the distance from hk to xy. Well, the distance formula says take the difference in your x's, so x, so x minus h, quantity squared, plus y minus k, quantity squared, is going to be equal to the rate. Well, we take the square root, and that's equal to the radius. But if we square both sides of this equation, then we get this equation. And that is the standard form for a circle, right, that we've talked about already. Note, if the center of the circle is at 0, 0, then I'd be plugging in 0 for h and 0 for k, and I would just end up with this simpler equation, x squared plus y squared equaling r squared. So let's take a look at this example. Let's say the point 1, negative 2 lies on a circle whose center is at negative 3, negative 5. Write the standard form of the equation of the circle. So let's get a quick little graph going here to see what's going on. So I'm such a visual learner. I want to see a picture of this. So in this case, we have the center of the circle at -3, -5, which is right here. That's the center. And the circle passes through the point 1, -2. All right, so it seems to me like the circle would look something like this. I'm just doing a rough estimate of this circle. So this is my center. It's -3, -5, and this is some random point on the circle, 1, -2. All right, so we don't know the radius yet, but we could find that. But I think I would like to just use my equation, x minus h quantity squared plus y minus k quantity squared equaling r squared. And I know that this is going to be x minus a -3 quantity squared, which I can really write as x plus 3 quantity squared, and then plus y minus a -5 quantity squared, which I could write as y plus 5 quantity squared, equaling r squared. But I don't know r, so I haven't found my equation just yet. But I do know that one point on my circle is 1, -2. So I could plug in 1 for x and -2 for y and solve for r. So let's try that. So that means I want 1 plus 3 quantity squared plus a -2 plus 5 quantity squared equaling r squared. So I get 4 squared plus 3 squared equaling r squared. That's supposed to be the equals. And so I get 16 plus 9 equals r squared. That's 25 equals r squared. So I do know that my radius would be 5, but I think that our equation is just going to be x plus 3 quantity squared plus y plus 5 squared equaling, is it equaling 5? No, it's equaling r squared, so it's going to be 25. All right, so that's one way that you can get the equation. You certainly could just use the distance formula straight up to find this distance here, but you certainly don't have to do that. All right. Okay, and so the last thing that I want to tell you from this section is that in the book they do point out that there are 3 main approaches to solving a problem. There's a numerical strategy. That's where you would construct a table and use a table to help you. Or there's a graphical strategy where you would draw and use a graph. Or there's an algebraic approach to solving problems where you're going to use the rules of algebra. And in this course, we're going to be using all 3 of these approaches to solve various problems. All right, some might, lend themselves more to an algebra approach, whereas others might lend themselves more to a graphical approach, and so on. All right, so that's it for this lesson. Thanks for watching.